example, we're going to, this time the cross section is not necessarily a disc or washer. Could be other shape, could be a triangle, could be a square. Okay. Example 7. Over here, we have a solid with a circular base. So the base here is a circle. And parallel cross section, so those cross section over here are going to be perpendicular to the base, and they are equilateral triangle. Equilateral triangle means the three sides are equal. So we try to find the value for this solid over here. So this is a computer generating picture of the solid. Okay. So here is some diagram. So the base here is a circle, and the cross section, each one of them are equilateral triangles. Each one of them is an equilateral triangle. So what will be the value for this solid? So we slice it this way. So we're trying to find the value for one slice over here. So we use the cross-sectional area times the thickness. So what would be the cross-sectional area here? Now, this point, this plane over here is going to cause this x-axis at this. Okay, so first, let's take the circle, the base circle here to be x squared plus y squared equal to 1. The solid here with a circular base of radius 1. This cross section over here is going to intersect with this base over here at this 9 over here. When this point, if we label this point x comma y, this is an x and this is a y. So the y over here is going to correspond to this. So the base of this equilateral triangle is going to be 2y. So this will be the base for this equilateral triangle, 2y. Now because this is 60 degrees, so the height for this equilateral triangle will be this y times tangent of 60 degrees. Tangent 60 degrees is square root of 3. So this height for this equilateral triangle is root 3 times y. So the area for this is going to be 1/2 times the base times height. So that will be 1/2 times the base times the height. Simplify this, you get root 3 times this quantity, 1 minus x squared. Okay. So this is the cross-sectional area here. Now we're going to find the value of this solid by integrating this cross-sectional area, okay, with respect to x. Remember this dx corresponding to the thickness for this slice here. So that is the thickness of each slice here is delta x. So that's why this is dx over here. X start from -1 and end at 1. So we integrate this cross-section area, x with respect to x, x go from -1 to 1. So this is the integral for this, representing the value for this solid here. Now notice that this is an even function and the symmetry of the upper and lower limit over here. So this integral is equal to twice this integral from 0 to 1. Now we find antiderivative of this. Antiderivative of 1 will be x. Antiderivative x squared is x cubed over 3. Evaluate this x go from 0 to 1. That will give us 4 root 3 over 3. So this is the value for the solid that we talk about. Next example, example 8. Find the value of a pyramid whose base is a square. Okay, the base here is a square with the side to be L. So this is L. Okay. And the height for this pyramid is this small h over here. Okay, so from here to here is h. So we want to find the value for this pyramid. Okay, so let's use calculus to do it. Okay, so we're going to slice this. So we're going to place this pyramid this way, and we're going to slice it vertically. Each slice over here, the cross section is going to be a square, okay? So what will be the cross-sectional area? Now let's label this point over here. From here to here, let's label this. The x-coordinate is x. The side for the square here, let's call that small s over here. Small s over here. Then we've tried to express this s over here in terms of this x over here, because the thickness for each slice is delta x. So later on, the integral will have dx. So it will integral with respect to x. So we'll try to express this s over here in terms of this x. So we see that this triangle and this triangle, they are similar triangle. So let's draw this. So this triangle and this triangle over here, they are similar triangle. If you take the ratio of the corresponding side, then the ratio will be equal. So what do we have here? So we have this x over here to the h over here. So this triangle and this big triangle, they are similar triangle. So if you take the ratio of the corresponding side or the corresponding height, so x over h will be equal to this s over l. Here, express this s over here in terms of x. So x over h is equal to s over l. Now we're trying to express this s in terms of x. So s is equal to x over h and then times l. Times l. Okay. So we got this. So s is equal to l times x over h. That one. So this cross-sectional area is the area of this square over here is equal to the square of this s. So squaring this, we're going to get l squared over h squared and times x squared. Now, to find the value for the pyramid, we're going to integrate this cross-sectional area with respect to x. The thickness here is delta x, so this is dx. X go from 0 all the way to h. Okay, this is h. So integrating this, notice that l squared over h squared, this is a constant multiple of this x squared. So you can bring it in front of this integral. Antiderivative x squared here is x cubed over 3. X here go from 0 to h. So substituting here, we got l squared times h divided by 3. So this is the value for the pyramid that we talk about. Notice that we don't need to place the vertex of the pyramid at the origin, like the one that we did in the last example. We can also place the base of this pyramid this way, okay? Then if we do it that way, we end up with this integral. The cross-section is still a square. We end up with this, but this time the thickness for each slice will be delta y. So that will be dy over here. And you're going to integrating this with respect to y. Y go from 0 all the way to h. You would end up with the same result over here. Okay. Example 9. A wedge is cut out of a circular cylinder of radius 4 by 2 planes. The first plane is going to be perpendicular to the axis of the cylinder. So the first plane will be this plane right here. Okay. The second one will be this plane right here. It's going to intersect with this horizontal plane over here at a 30-degree angle, at the angle of 30 degrees. So we're trying to find the value for this wedge over here. Okay. So we place this x-axis this way, and the y-axis this way. Okay. Now, the equation for this semicircle will be y equal to square root of 16 minus x squared. Because for this circle, it is x squared plus y squared equal to 16. Because this circle here has radius 4, now for this semicircle here is the upper half of this circle. So y is equal to positive square root of 16 minus x squared. With the y here going from -4 to +4. Now, to find the value for this solid, this wedge here, we're going to slice it this way, okay, vertically. This cross-sectional, each one is a right triangle, like this, with this one being 30 degrees. So let's find the cross-sectional area here. So it will be 1/2 base times height. The base over here is going to be correspond to the y coordinate of this one. So it is going to be square root of 16 minus x squared. What about the height? The height over y is going to be tangent of 30 degrees. So this height here, BC, is going to be this y times tangent of 30 degrees. Tangent 30 degrees is going to be 1/√3. So BC, the height is going to be square root of 16 minus x squared divided by square root of 3. So the cross-sectional area is going to be 1/2 base times height. So 1/2, this is a base, which is a y here. This is a height, which is the BC over here. Do the algebra, so that's 16 minus x squared over 2 square root of 3. Now we can find the value for this solid over here by integrating this cross-sectional area with respect to x. Because each slice here, the thickness is going to be delta x. So that is dx here. X go from -4 to +4. Now notice that, again, this is an even function. And because the symmetry of the upper and lower limit, this integral is equal to twice the integral from 0 to +4. So the book had a mistake. So let's fill this in. So that's equal to twice this integral from 0 to 4 of this 16 minus x squared over 2√3 dx. Now notice what happened here is this 2 here cancel. That is going to give you this one over here. Okay. Now we find antiderivative 16, that is equal to 16x. Antiderivative x squared is x cubed over 3. Evaluate this, x go from 0 to 4. Do the calculation. So that's 128 over 3√3. So this is the exact answer over here. Now, finally, to help with the homework, so I put down this formula. The derivative of tangent x is secant square of x. Derivative of secant x is secant x times tangent x. Remember our trick, the SST. Antiderivative tangent x is ln of absolute value of secant x. So we covered this long ago in class. So I just put them down here just to refresh your memory, and those will be helpful when you do your homework. Okay, so that's the end of our lesson today.